All right, let's dive in. Today, we're going to talk about the invisible force that powers pretty much everything you see around you, alternating current. We're going to peel back the layers on how this dynamic, constantly shifting energy actually works, from the absolute basics all the way up to the giant systems that run our modern world. So here's the game plan. We'll kick things off with a fundamental showdown, AC versus DC. Then, we'll get to know the main players in any AC circuit. After that, we'll uncover the secret behind something called an LCR circuit, talk about what power really means in AC, and finally, see how transformers are the unsung heroes that get all that power to you.
All right, first things first. To really get a grip on alternating current, the best place to start is actually with its simpler cousin, direct current, or DC.
Okay, so it really all comes down to how it flows. Think of DC, like what you get from a battery, as a steady river just flowing in one direction. Super simple. But AC is more like the ocean tide. It's constantly moving back and forth, its strength swelling and fading in this perfectly smooth, rhythmic cycle. So what does that back and forth actually look like in the real world? Well, in a lot of countries, the standard frequency is 50 hertz. Get this. That means the current flips from positive to negative and back again 50 times every single second. It's completely reversing direction 100 times per second. It happens so unbelievably fast that you can't even see your lights flicker. So, you've got this current that's constantly changing, right? How in the world do you measure its power? I mean, if you averaged it out, it would just be zero. That's where something called the root mean square, or RMS value, comes in. It's basically a really smart way of asking one simple question. If I wanted to get the same heating effect from a DC current, what value would that DC current need to be? It gives us a real, practical number for AC power. And you actually see this every single day, you just might not realize it. When you look at your wall socket and it says 220 volts, that's not the peak voltage the current hits. Nope, that's the RMS value, the effective, useful voltage that we actually care about. Okay, so we've got this wild, oscillating current. Now, let's meet the three main characters, the components that try to control it. And I really do think of them as having their own unique personalities when it comes to dealing with AC. Each one handles AC completely differently. First up, the resistor. He's the simple, no-nonsense guy. It just provides resistance, and the current and voltage march along perfectly in step, totally in phase. Then you've got the inductor, a coil of wire that just hates change. It fights against the current shifts, which causes the current to fall behind the voltage. It lags. And finally, the capacitor. This one's all about storing and releasing charge, which gives the current a head start, making it lead the voltage. Each one creates its own special timing shift. So we've met the players on their own, but what happens when you put all three of them together in the same circuit? An inductor, a capacitor, and a resistor? LCR. This, right here, is where the real magic happens. But before we dive into the nitty-gritty, just think about this for a second. Right now, the air around you is flooded with hundreds of different radio stations, Wi-Fi signals, cell signals. So how does your phone or your car radio pick out just one of them and ignore all the rest? Well, the answer is the magic of an LCR circuit. So when these three are all in a circuit, they create a new combined opposition to the current. We call this impedance, and we label it Z. It's not just simple resistance. It's this dynamic, total opposition that includes the push and pull from the inductor and the capacitor. And it actually changes depending on the AC's frequency. Okay, here is the secret sauce. Remember how the inductor and capacitor are basically opposites? One makes the current late, the other makes it early. Well, there is one special frequency where their effects perfectly cancel each other out. It's like a perfect tug of war where nobody moves. And we call this incredible moment resonance. And that perfect sweet spot, that's what we call the resonant frequency. And look at this. Its value is decided entirely by the inductor, L, and the capacitor, C. This is huge. It means if you can change the inductor or the capacitor, you can change the resonant frequency. You can literally tune the circuit to listen for a different frequency. So what's the big deal? What happens right at that magic frequency? Well, since the inductor and capacitor's opposition have vanished, the circuit's total impedance just plummets to its absolute minimum. And what happens when opposition is low? Current goes through the roof. It's like the circuit throws open the gates and rolls out a red carpet, but only for that one frequency. Everything else gets blocked. And this one idea is the bedrock of pretty much all modern wireless tech. All right, so we figured out how to tune in to a specific frequency and let the current flow. But is all of that energy actually doing anything useful? This brings us to a super important idea: power in AC circuits. Now, in a simple DC circuit, power is just voltage times current, right? Easy. But with AC, it's not so simple. There's this extra little piece to the puzzle, cosine phi, also known as the power factor. And that little phi is just the phase angle, that timing difference between voltage and current we were just talking about.
Think of the power factor as an efficiency score for your circuit. It tells you exactly what percentage of the energy flowing through the wires is actually getting converted into useful work, like heat or light. A perfect score of 1 means it's 100% efficient. A score of 0 means energy is moving around, but absolutely no work is getting done.
And that brings us to this really weird, cool idea called wattless current. If you have a circuit with only a perfect inductor or capacitor, the timing shift is so big that the power factor is 0. That means you have current flowing, but no actual power is being used. It's like the energy is just sloshing back and forth in the wires, never actually getting used for anything.
Okay, let's pull back from the tiny components and look at the big picture. Let's talk about the absolute workhorse, the unsung hero that makes our entire modern electrical world possible. I'm talking about the transformer. The whole thing works because of a really elegant principle called mutual induction. First, you run AC through a primary coil of wire, which creates a constantly changing magnetic field. An iron core then guides that field over to a second coil. And because that magnetic field is always changing, it induces a brand new AC voltage in that second coil. There's no physical wire connecting them. It's pure physics magic. And the best part? Controlling the voltage is brilliantly simple. If your second coil has more turns of wire than the first, the voltage goes up. That's a step-up transformer. If it has fewer turns, the voltage goes down, a step down. You can't get something for nothing, of course. Power stays the same, so voltage goes up, current has to go down. It's a perfect trade-off.
Now, in a perfect world, that's the end of the story. But in the real world, nothing's 100% efficient. Transformers lose a little energy. Some of the magnetic field can leak out. It takes energy to keep magnetizing the core. They physically vibrate and hum, and the copper wires themselves get hot. Still, they're incredibly efficient, often over 99%. So why should you care? Why is this one device so absolutely critical? Because it's the key to our entire power grid. Power plants use giant step-up transformers to blast electricity out at super high voltages, which is way more efficient for long distances. Then, transformers on poles in your neighborhood, and even in your device chargers, step that voltage way, way down to a safe level you can actually use. And that leaves us with a pretty incredible thought. When you really think about it, a transformer is a form of wireless power transfer, right? It sends energy across a gap using a magnetic field. So, if we've perfected this on a small scale, inside a metal box, what's stopping us from one day taking that same exact principle and using it to power our entire world without any wires at all?